Hello, I'm Mr. Rast, and this is the second lesson in the topic of energy and states of matter. In this lesson, I'm going to hopefully get you guys to understand what specific heat is. So before I get into that, let's talk about a little bit of prior knowledge that you should have before you come in here. Just some simple questions. Here's two bowls, A and B. Take a good look at them and the temperatures of them. Which bowl would feel warm to your hands? And which bowl would feel cool? Next question, same thing. In number 2, which bowl would feel warm to your hands? And which bowl would feel cool? So if you had your hands in both bowls. If you take a look at this, in the first example, you would probably say B would feel warm to your hands and A would feel cool. And in number 2, you would say A would feel warm to your hands and B would feel cool. Next example, a person from England tells his friend from Italy that the weather in England is somewhat warm. When the friend arrives for a visit, he finds that he is uncomfortably cool wearing shorts that he packed. What would be a more effective way for a person in England to explain the weather? And I think the prior knowledge and the point you might be seeing where I'm getting at is in number 3, you would say, instead of saying it's cool because it's generally cooler in England than it is in Italy, he should give you the temperature. And being hot or cold is a relative term. So let's go back to number 1. 30 degrees Celsius was A. And in that one, we would have said 30 degrees Celsius would feel cool to your hands. But in the second example, 30 degrees Celsius would have been the one that was warm to your hands. So sometimes 30 degrees Celsius would be considered warm, sometimes it's cool. The point of the matter is it's all relative. It's relative to the situation that you're used to or what someone else is used to when we say hot or cold. So we're going to quantify temperature and do our best not to use terms of hot or cold in this class and actually use quantifiable terms for temperature. And by the way, what is temperature? This is a really difficult question to ask most people just walking around. If you ask what temperature is, they'll say, well, it's how hot or cold or something is. And you say, well, what is hot? What is cold? What is temperature? And people know what it is, but they can't quite explain. What temperature actually is, it's the average kinetic energy of all particles within an object. The hotter an object is, the faster the particles are moving. And the cooler it is, the slower they're moving. Why things feel hot to us is because the particles of something hot are moving faster than our particles, and those particles are colliding with ours and speeding our particles up in our skin, and we feel hot. We're getting energy transferred to us. On the other hand, if we feel cold, the particles on our body are moving faster than maybe a cold day, and we're heating up the air around us. We're losing energy as our particles are warming up the ones around us, and because we're losing that energy, we say it's cold. But it has to do with motion. It has to do with kinetic energy. If you forgot, kinetic energy is the energy of motion. So, like I was saying, we're not going to say hot or cold. We're going to quantify it, and we quantify it with devices called thermometers or a thermometer. A thermometer is a device that measures temperature, and it does this because as things speed up the kinetic energy, the molecules vibrate faster and faster and faster, and if you have a long narrow tube, that vibration can make the molecules have to climb the tube to get further and further apart from each other as they're colliding. And that's the whole physics behind, simply put, behind thermometers. So most thermometers rely on expansion. That's what I was saying, because the kinetic energy of the molecules moving, as the temperature increases, the particles in the liquid inside the thermometer gain kinetic energy and they begin to move faster. With the increased motion, the particles begin to move further apart and rise up the narrow tube. Got it? All right. Refrigerator thermometers do the same thing. They rely on expansion. And you take a long piece of metal and you coil it up. And the metal can still expand and contract slightly. So they coil up a very long piece of metal so that a little expansion and contraction as a coil can be noticeable. You put a needle on that, and if you see here, you might have a thermostat where if the needle, let's say it's a heater, and so we've got our refrigerator. So we've got the thermostat set here, and as it warms up, the needle crosses and it clicks it. That turns the refrigerator on, and then it gets cold and the metal condenses and it comes back and it clicks off and it turns it off. So we can sometimes move a dial back and forth. A lot of refrigerators, older refrigerators work like that, or heating, air conditioning units in your house or heating units in your house work like that, where there's something going to trip it, and that's relying on expansion as well. Digital thermometers use electricity to measure the temperature, and we'll get into that later when we talk about electrons and electrochemistry, but not right now. So temperature is a measure of kinetic energy. We use a little tube, and then we can arbitrarily put numbers on there and come up with different scales. So it's worth noting the different scales and how to convert in between them. If you want Fahrenheit and you have Celsius, you multiply your Celsius by 1.8 and then add 32 to that. So let's think. 0 degrees Celsius, 0 times 1.8 is 0 plus 32. So 0 degrees Celsius when water freezes is 32 degrees Fahrenheit. That makes sense? Rearranging this equation to solve for Celsius, it would be Celsius equals Fahrenheit minus 32 divided by 1.8. So if we wanted to know the Celsius and we have the Fahrenheit, we first have to subtract 32 from that number and then divide that number by 1.8. And then we would get the Celsius value. So again, water freezes at 32 degrees Fahrenheit. So 32 minus 32 is 0. 0 divided by 1.8 would be 0. Another scale that we use for temperature, and we use most often in science, is the Kelvin scale. And the Kelvin scale is based off of absolute zero, which I'm going to get to that. In other words, zero, there is nothing colder than 0 Kelvin. We can have negative 5 degrees Celsius and negative 5 degrees Fahrenheit, but you can't have negative 5 degrees Kelvin, and I'm going to get into that in a moment. But this scale is Celsius plus 273. You add 273 to your Celsius and you're in the Kelvin. So inversely, if you take Kelvin and subtract 273 from it, you would then be in the Celsius temperature. And here's just a little practice with converting temperatures. See if you can do this. The highest atmospheric temperature ever recorded on Earth was 57.8 degrees Celsius. I believe this was in California, Death Valley. Express this temperature both in degrees Fahrenheit and in Kelvin. So you can pause the video and give this a try, and then start it. See if you got it right. Let's see how you did. So the first thing you do is pull out information that you know in the question, and we know that the temperature in Celsius is 57.8 degrees Celsius, and we want to solve for the Fahrenheit and the Kelvin. To solve for your Fahrenheit, you would multiply 1.8 times the Celsius and add 32 to it. To solve for your Kelvin, you would just add 273 to your Celsius. So let's solve it now. So the first thing is that I always do in word problems, I write what I know. The second thing is I write down what kind of formulas I need to do. And the third thing is I solve it. So the Fahrenheit, the temperature in Fahrenheit would be 1.8 times 57.8 degrees Celsius plus 32, which is 104 plus 32 is 136 degrees Fahrenheit. That is ridiculous. And in Kelvin, it would be, just adding 273 to it, would be 331 Kelvin. Wow. Okay, So just a little practice with temperature conversions. I wanted you guys to be exposed to that. Like I was saying before, the Kelvin scale is based off of something called absolute zero. So temperature is the kinetic motion of particles. So if particles are moving around, the potentially you could think they can get hotter and hotter and hotter and hotter. Like how fast can they actually move? But if we go back, we could talk about how fast they actually move, but that's not what we're talking about today. Theoretically, you can just think it gets faster and faster and faster. But if you go in reverse, you can get slower and slower and slower. So how cold can you possibly get? Absolute zero would be the coldest you can get, where there'd be minimal or if no motion whatsoever in the particles, whatsoever. This would be somewhat hypothetical. We can extrapolate where it would be, but we can't really get to it because anything that's measuring it would have to have some kinetic energy to measure it. You couldn't insulate it enough without any signal getting out of it. But we can get extremely close to it. So absolute zero is when the particles don't move anymore. And so the good thing is, if you have no motion in the particles, you have no energy. So 0 Kelvin would represent no energy, which is good that's where we use it in calculations, because if you happen to have a 0, that will make all your multiplication values void. But it's good in the Kelvin scale because it is 0 means no energy. So now we got our background on what temperature is, that we understand that it's a measure of kinetic energy. We use thermometers to measure it. Let's talk about what specific heat is, because that's really where I'm driving you, but I want to give you some background to understand what specific heat is. So specific heat is the amount of energy transferred as heat that will raise the temperature of a kilogram of a substance by 1 Kelvin. The symbol for specific heat is a lowercase c. Its units are joules per kilogram Kelvin. Sometimes students think that's a formula. Those are just units, joules per kilogram Kelvin. So specific heat is a constant, and it has joules, kilogram, and Kelvin in that constant. Joules over kilogram Kelvin. How much energy is joules per kilogram Kelvin? So let's talk about specific heat. What really is this? And I'll give you hopefully an example that you can somewhat relate to. Pretend it's a hot day. It's a hot day, and the water remains cool, and the cement on a hot day, the water remains cool, and the cement around it is not. So think that it's a hot day. You're at a pool, and you're walking around, and the cement is so hot you're just doing that dance on the cement. You're ow, 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 and you're running, and you get over to the pool. You stick your feet in the water, and you're like, oh, relief, relief. And so the water and the cement are both only being heated by the sun. The energy of the sun is heating both the water and the cement, but the cement is releasing so much more heat. The cement got so much hotter than the water did. Okay, this has to do with specific heat, and I'll tie it together in a moment. So you're still at the pool, and the party's going on, and you've been out of the pool for a while. The sun goes down, the moon is out, and now it's really easy to walk on the cement. There's very little energy on the cement. In fact, if you were to sit on the cement, you might even find it darn right cold, and you'd find more warmth if you put your feet in the pool. The pool might be a little bit warmer now than the cement around it. This phenomenon is due to the difference in the heat value, the specific heat value of the water and cement. Water has a very high specific heat value, so it takes a lot of energy, like for in this instance the sun, to heat up that water. It doesn't change temperature quickly. Where cement has a much lower specific heat, so the energy that it gets will change the temperature quickly, but it also will lose that temperature quickly. Water is hard to heat up, and it's also hard to cool down. It holds that temperature well, which is good because the chemistry of our bodies is mostly water, and it's good that water has a high specific heat. We don't go outside and freeze or boil just because the conditions are out there like that. It takes a lot of energy for our temperatures to change, and the proteins in our body would denature if it got too hot. Our enzymes react at certain temperatures we react optimally. So having water in living organisms is very important, and that's because of the specific heat of water. It keeps our reactions at a constant, reliable temperature. So here's some actual values of specific heat. Example, water has a specific heat value of 4,186. And remember the units, I said it's 4,186 joules per kilogram Kelvin. That would make a kilogram of water, it would take 4,186 joules of energy to turn 1 kilogram of water by 1 degree Kelvin, or 1 Kelvin. On the other hand, gold has a specific heat of 129. So it only takes 129 joules of energy to change the same mass, 1 kilogram of gold, by 1 Kelvin. So gold will heat up much faster than water, and it will cool down much faster. These are some constants that I will be handing out to the class. If you're in my class, you should have a copy of this. Otherwise, I'll make this available as a download document on the website. But these constants, these are just constants. And like I gave you 2 examples here. Water has a constant of 4,186 as a liquid, but when water becomes a steam, its specific heat actually changes. Here's a great example of phase change and how it changes the chemistry of something, the physical properties. So 1,870 is the specific heat of steam, where water, it's much higher. We have ammonia, aluminum, gold. You can see things like mercury, which thermometers used to be made out of, has a very low specific heat, which is good thing to put in a tube, because it would slight changes would make mercury go up and down that thermometer pretty well. So materials with a high specific heat require more energy to change their temperature and take longer to cool off. The equation for specific heat is, when we talk about how much energy is it take for something to happen, it's the energy is equal to the specific heat times the mass times the change in temperature, which is represented as energy equals C, specific heat is lowercase c, times m, lowercase m, that's mass, and this triangle T. This triangle, whenever I show you this triangle in the class, it's a delta symbol. It means change in, so the change in temperature. And something I'd like you guys to note is that when we talk about change, whenever you see this triangle, it's always, change is always, you might want to write this in your notes, it's always the final value minus the initial value. Change is always final minus initial. This is important because sometimes change is a positive change and sometimes it's a negative change. If you think about your bank account, the final value of your bank minus the initial, your change, let's say I had no money in my bank account and I just got $100. So my final is 100. I initially had 0. So that would be a change of positive 100. Let's say now I have $100 and I spent it all. I took it out of the bank and spent it. So now my final is 0, but I initially had 100. So that would be 0 minus 100. That would be negative. So it's important to note that it's always final minus initial. And you might have positive or negative changes. So that can come into play and cause problems for students on tests and quizzes. They'll miss questions because of that. They'll just take the difference. They won't really care which is the final, which is initial. Keep this straight. All right, here is a specific heat question. How much energy must be transferred as heat to the 420, or I'm sorry, how much energy must be transferred as heat to the 420 kilograms of water in a bathtub in order to raise the water's temperature from 25 degrees Celsius to 37 degrees Celsius? See if you pause the video and see if you can figure out how to do this from your constants. If you're not sure, we'll just work it out together, but see what you can do. If you don't know where to start, the first thing I always do is write down what do I know from the question. The first thing is what do I know from the question. You'll notice I'll have these 3 steps constantly over and over and over in this class. So you can start somewhere, even if you seem like this question seems out of your grasp. You still know just reading the question how much energy. So you know energy. I'm solving for energy. You also know that there's a mass here, 420 kilograms. You should know grams, but at this point is a measurement of mass. I also know a change in temperature, and like I said, it's final minus initial. It's going to end at 37 degrees Celsius, and it's starting at 25 degrees Celsius. So the change in temperature is 37 minus 25 degrees Celsius, which is 12 degrees Celsius, which happens to also be 12 Kelvin. Now this confuses people, so I'm going to walk you through this. A change in Celsius is equal to a change in Kelvin. And I know that I told you that 37 degrees, oh, this isn't writing well, 37 degrees minus 25 degrees equals 12 degrees Celsius. Equals 12 degrees Celsius. I didn't want that to pop up yet. And I said it's also Kelvin. Well, we could change these into Kelvin because it's Celsius right now, right? If I changed it into Kelvin, I would just add 273 to these numbers. Add 273 to this number. And then I would have it in Kelvin, but if I'm just subtracting that, by adding the 273 to both of them, I'm adding it to here and adding it to here, but I'm subtracting these values. There's nothing there. So anyways, let's just add it up and just see what it is. That's a 3, carry the 1, we've got a 1 and a 3. And then over here I've got a 5 and 3 is 8, 9 and 2. So in Kelvin, it would be 310 minus 298, which is also 12 Kelvin. Okay, so just kind of showing you that a change in 12 Celsius is also a change in 12 Kelvin, and that's how that works out. Okay, so I'm going to, oh yeah, it's just jumping all over the place. Erase this stuff here. All right, so another thing that we know for this question is that we're dealing with water. So we're going to look at the specific heat of water, and we can use that table that I said that we have. And if you're just using the video here, then you're going to have to scroll back to this page here. The specific heat of water is 4,196 joules per kilogram Kelvin. So we're using water. We get that specific heat. We look at our table. We know our energy. Our equation is energy equals Cm delta T. We're going to plug in these values into our equation. So you might think, I don't know where to start, but if you just start pulling things out that you know, and then look at the equation that you know, it's like all of a sudden you're like, wait a second, I do know where to start. I can do this. So I'm going to plug in my specific heat here. I'm going to plug in my mass here, and my change in temperature there, and make sure when you do your work in my class, you show your units and you cancel out your units. No work, no units, no credit in my class. So we have kilograms canceling with kilograms, Kelvin canceling with Kelvin. We multiply these together, and with proper significant figures, it's 21 million joules. Got it? I might write 21 megajoules, because if you remember in the first topic we talked about prefixes, 21 megajoules would be a little easier way to do this. Or also in the first topic we talked about scientific notation, so we might move the decimal place over here and say 2.1 times 10 to the 1, 2, 3, 4, 5, 6, 7. So it might be 2.1 times 10 to the 7th joules would be another acceptable way of writing this. All of them are correct, by the way. Okay, your classwork is some specific heat problems. You're going to need that table if you are using The video, you might have to kind of figure out at what number what time it was on. Otherwise, look at the website. You can download one of the handouts. And if you're in my class, you should have a handout in your notebook. So you'll need that because if you look at the first question, how much energy is needed to raise the temperature of carbon? You need the specific heat of carbon. You got to look it up. And the second one, we're dealing with silver. It's a different specific heat. Here I've got water. I've got aluminum over here. And this one, number 5, check this out, an unknown material. So you're going to use these properties to see if you can figure out what the material is. You're going to solve for specific heat and then look at that table and see if you can figure out which one it is. So anyways, give this a try. And if you have any questions or problems or need help, let me know. That's what I'm here for. Talk to you soon.